from Fahrenheit to Celsius you have. Does that make sense? So most the things you're going to see are going to be metric for Celsius. So get used to that. Okay. So temperature per watt, Celsius per watt. These are ratings. Does that make sense? So watch out for these things. This is thermal resistance. It's again, it's measured in that manner. And notice here, dissipation is the inverse of what? Thermal resistance. Does that make sense? And that one would be in watts per Celsius, right? It's mathematically the inverse. Okay, we'll get to that in a minute. And then we have some other characteristics that we're going to be looking at, which are related to these max values here. But I'm going to be looking for the DC beta. Remember beta? Right? So, but under certain circumstances, what my BC beta might be. Right? So we could see here, these are the values right here. And I'll show you where to estimate as we start building the circuit. And then we'll see if indeed in the lab we're going to be really close. Does that make sense? The idea is when you build it, you want to be as close as possible to your estimation.
So the on characteristics is the DC beta?
No, I haven't drawn the characteristics yet. Well, we have diagrams for characteristics. That's at the end. We'll worry about it. So now let's go back to the max ratings. And notice here, it's going to tell you emitter voltage and collector to base voltage. So collector to emitter voltage. This is the collector, this is the emitter, and this is the base. They're telling you the max you should have from here to here is what? 40 volt DC. Does that make sense? I'm nowhere near that with that power supply 15 in my train. If I had a power supply that can go to 60, 70, 80, then I'll have to worry about that and compensate with the resistor to lower it. Does that make sense?
Yep. Across which sector? BDE? For the maximum.
So this is between collector and emitter. So collector, emitter, VCE max. So VCE max is the voltage from here to here. You with me so far? We don't want that to see 40. Does that make sense?
Yes.
Good. In my case, if the transistor is cut off, what does that mean? There's no current collector. You with me so far? Mm-hmm. Then what is the voltage drop against VC based on this configuration? Without knowing what the resistor is, doesn't matter.
40 would be 15 volts.
It will be 15 volts. It's an open circuit. So I know right there and then I've met the requirements for max. Does that make sense? So far so good?
Yeah, it's 15 because...
Yeah. So this supply is just less than half the max voltage that's needed between what? The collector and the emitter. Okay. How about collector to base? Well, that's the difference from here to here. Usually that's not an issue right now. So let's look at the emitter base, which is from what? From here to here. That should not exceed 6 volts against that 0.7 direct. Does that make sense? So that means if this transistor is off, what would be the voltage from here to here? 15. Will that be a good thing? No. Well, is it? Or is the transistor, or would it be in forward? Would it still be in forward? So VB max 6. Okay? So we got a problem there. Do you agree? With the 15 volt on that end. So we really need to reduce the voltage here. Do you agree? Right? Okay. Well, we'll worry about it in a minute. So collector current. Now that's important. 200 milliamp DC. That means the current going to the collector, IC, should not exceed, if your transistor is saturated or working, should not exceed 200 milliamp. That's the current that goes through the collector. Does that make sense? Okay. So what else? Temperature stuff, we're not worried about. I'm worried about these values for now. Why? Because I'm trying to bias the transistor, get it to work. Does that make sense? Get it to work in a DC environment. Later on, we get to bias it for AC, and for that, we need to go down to the small signal characteristic right here. Right, so we've got a whole week for that, another week getting here. So it's a complex piece of equipment. Does that make sense? So we're going to get to that when we're ready. So first, we want to make sure that we are within working range. Here, I'm going to put a question mark here because most likely I'll change it. Do you agree? Right? Okay. So now it's a matter of where do I want to be? I usually like to be about 1/10, if not less, of this stuff. Does that make sense? Right? So, the one thing I start analyzing, what I like to analyze first is this part. And I go through to the extremes. One extreme, we know if it's cut off, which means the transistor is not operating, it's an open, then the voltage from here to here is 15. I'm good with that. So VCE of cutoff will be equal to 15 volts. VCE of saturation typically is going to be close to 0 volt. That's because you have IC max going through. Does that make sense? So we have these two conditions, cutoff and saturation. Let me write them up here. I mentioned them before, cutoff and saturation. And we want to be somewhere in between if we're going to use this transistor as an amplifier. We want to be at cutoff and saturation when we're using it as a switch. Does that make sense?
Why is the saturation 0?
Right. So why is saturation going to be 0? Which means that means you will have maximum current in here. You want this junction to collapse. And which means now, what is the maximum current you can draw from here? So when this is open, what is IC of cutoff? Anybody?
0.
It'd be 0 amp. Does that make sense? You have no current. So here, IC of saturation is going to be equal to VCC. Let's call this one VCC. Divided by RC. If this is 0, it's a short, isn't it? So now, Kirchhoff, I only have what? RC against the resistor. Do you agree? So that's a great resistor to figure out. Where do I want to be to get started? Does that make sense? That's my starting point. I can decide there any current below 200 milliamp and work. Does that make sense? So I'm evaluating RC on the saturation value, which means now I got to reevaluate RB to bring it down to operation. Does that make sense? And that's going to depend on beta of the transistor because there's a relationship between IB and IC. Remember that. When I sent you to a corner, I asked you to go over and over the relationships, right? Right? So now we know is a relationship between IB and IC. We know that IC is equal to beta IB. This is fundamental for this device. Do you agree? So far, so good? So I am going to go with saturation. And I'm going to have to decide, based on this 200 milliamp, where would I want to be? You know, you look at your bag of components and you say to yourself, what kind of resistors do I have? Do you agree? You can work that way. 1K is very common. I have a 1K resistor. So what is 15 divided by 1K?
15.
15 milliamp. Can I saturate my transistor at 15 milliamp? Sure. It all depends how you set it up. Does that make sense? Will it still be in good operation? Absolutely. I'm not even near the 200 milliamp max. Do you agree? So on a load line, if I'm comparing VCE to IC, I am looking at the IC of saturation equals to VCC divided by RC. And in my case, if I pick 1 kilo ohm, right? I could have picked higher, which means my current will be lower. I could have picked lower resistor, my current will be higher. Does that make sense? I know my range. I know that I shouldn't exceed 200. Anything else is valid. You agree? Okay. Good. So now, with at 1 kilo, IC of saturation is equal 15 milliamp. Do you agree? So, this here is going to be 15 milliamp. And this here will be 15 volts, VCC. My load line is going to look like this. Straight line here. So my operating point is going to be anywhere around here. Do you agree?
Yeah.
But that depends on what I do here, because I can throttle IC with IB. Do you agree? So far, so good? Good. Now, what's going on here based on that 15 volts? That's a problem. Right? Because if it's an open, this is still subject to 15 volts. Do you agree? Okay. So what if I put a 5-volt here? Okay. I can work with that. And let's say we are at saturation. We continue with that scenario. Does that make sense? We continue with that scenario. And let's say we are indeed at saturation. And that means I do have an IC of 15 milliamp. Do you agree? Right? Good. So that means I'm going to have a certain IB value. We're equal to IC over beta. Do you agree? Now, we don't know beta. We could see it in the spec sheet in a minute. Does that make sense? That the voltage drop here, let's call it VRB, is going to be equal to IB times what? RB. Do you agree? Yeah. What else about VRB we know? If I do Kirchhoff in here. If this transistor is in operation, I should have 0.7 volt for VBE. Do you agree? And let's call this one VBB. So I know that VRB is going to be equal to VBB minus VBE equals IB times RB. What I'm interested in is what is RB. Do you agree? So RB is going to be equal to VBB minus VBE divided by I, which is really equal to what? If I were to convert it, take my ID, so that would be IC times VBB minus VB over beta. You see how I came up with that formula? Let's see. Beta times divided by IC. Did my gotta be careful with my division. Now, I actually, this is correct. And the reason I know I was wrong is I was looking at voltage times current. That's power. Voltage divided by current is resistance. Beta times that resistance. Does that make sense? That means RB is going to be equal to beta times, let's say, whatever VBB is, minus 0.7 volt estimated, divided by, and in this case, at saturation, if I want to reach saturation, I can find what RB is. So that is going to be my, think about it. Is this going to be my max RB or min RB?
Max.
Think about it. I'm getting a max IC. I'm going to end up with max IB. Do you agree? So how do I reduce the current? You're going to have to start increasing the resistance. This is min RB. Does that make sense? This is the minimum RB you need to get saturation. Does that make sense? So divided by 15 million, 10 to the minus third. This is going to be RB min of saturation. Any lower than that, you're going beyond saturation. Does that make sense? Well, you're not going to operate anyway. So anything higher, yeah, that's going to move the point over on the load line. Does that make sense? Okay, does everybody understand the math versus the physics? Right? They're together. I can't escape it, right? Okay? So that means, yeah, I want to be at lower currents to be somewhere in this line, somewhere in the middle. I will try to avoid being here or here as much as possible. We like to be, if it's a really nice amplifier, I like to be right smack in the middle. Why? Because later on, when we start injecting AC signal at the input, we want maximum swing at the output. Does that make sense? Okay? Maximum swing on the positive and negative of the wave as we're going through it. So, all right. So now we can, okay, figure out, okay, so what do I have? I have VBB at 5 volts. So let's do an estimation. RB then equals beta, and that would be 5 minus 0.7 is how much? 4.3? 4.3 divided by 15, everything 10 to the third. You with me so far? Bring out the 10 to the minus 3 up. So what is 4.3 divided by 15? Any idea?
28, 23, 0.28.
0.28?
Yeah.
0.3?
Yeah.
10 to the third. Can I do that? Just leave it here for now. Now, I don't know what beta is. Do you agree? That depends on the transistor and where it's operating in. What range are we operating in? Well, I have some numbers here. Let's go to beta. Here's beta. So around IC of 10 milliamp. That's pretty darn close right there. Do you see this?
Yeah.
Around that, at a low voltage, almost at saturation, because VC is saturation should be 0. Does that make sense? It's telling me about one. It's 150. I would go for 150. Does that make sense? So I'm estimating my beta RB bin approximately equal to 150 times 0.3 10 to the minus third times to the third. So go ahead and multiply 0.3 by 150. What do you get up with it?
45.
45 kilo. We're going to try it. We're going to see if we're within the ballpark.
How do you find the beta again?
The beta, found myself right here. I'm around 10 milliamp. Does that make sense? Close enough to 0, 1 volt. It's going to vary between 50 and 150. You with me so far? I have a tendency to go to the higher number. You will see why. Does that make sense? So I know at worst it's 150, or at best, we want it to be at best in there. At worst, it will be at 50. Does that make sense? So we can see where it might be. So this is mid, max. So is everybody seeing now it's totally different the way we do estimations and so on than what you've done before, where everything was precise because you was just following Ohm's law or Kirchhoff. Or now you do an engineering. Does that make sense? It's a little bit of art and science involved. So you need to know the science behind it before you start, okay, say, I'm going to be right around here. But that comes with experience. Does that make sense? You can learn that by being in the lab. And I mean hours and hours in the lab. Okay? So, all right, I'm going to build it. I'm going to build it and see if I'm going to get values that are this close. And then try to get the operating point to the middle by increasing RB. You with me so far? So what I'm going to be playing with is which one? RB. Based on this scenario. You with me so far? Okay. All right. And let's go ahead and do it. So let me just create a directory. And
No, you just leave it that way. It's really information. But mine is missing that exactly. I think it's beta.
Is he on Senai?
God, that's right. That's a different.
and I'll be giving you this file when I'm done. So pay attention. Pay attention. I need you to pay attention. You will have a chance to do this. So just watch how I'm doing this. Okay. I'm going to pull my transistor. Start with that. And I'm going to pull an NPN transistor. That looks good. I'm going to say, okay, I'll just put it in here. Let me just make it a little smaller here. Yeah. So far, so good? Then